Hello. In this video, we will take a look at how we can construct a new design in Design Expert and also take a tour of the Design Expert software to check out how we do the analysis. So I'll try to keep this as short as possible, but still give you a few details about the software and important steps in constructing the design and also in the analysis. And I thought we were going to use the battery design experiment that we considered in previous videos already. So, and this example is given as example number 5.1 on page 192 in the 8th edition of Douglas Montgomery's course book, Design and Analysis of Experiments. This design is a factorial design with two factors where each factor is on 3 levels. So to construct this design, we will click the new design option here. The software jumps directly into the regular 2-level designs, but since we have 3 levels on each factor, we have to choose something differently. So in this case, I will go with multi-level categoric design. So this is also known as a general factorial design for between 1 to 12 factors, and each factor may have different number of levels, and all the factors are treated as categoric. In this design, one of our factors is the material type is categoric, and the other factor is temperature, which is a numeric factor. But still, I'm going to use this option here. There might be other options in this software for constructing this design, but I'll go with this one. Okay, so we will have two categoric factors, and let's call factor A material type. We don't have any units for that factor, and it's a nominal scale, so there's no real difference or order between the material types. And we have 3 levels, 1, 2, and 3. The other factor is the temperature, and that we can call that an ordinal scale, and we still have 3 levels. Sorry, I'll skip this one. The units. We have degrees Fahrenheit here. I'll write this deg F. And yes, we have the first level is 15 degrees Fahrenheit, 70, and 125. And then if we look at the example and the table, we see that we have 4 replicates for each treatment combination. So we have 9 treatment combinations and 4 replicates for each. We'll do this by clicking 4 replicates here. And this will amount to 36 runs in total in the design. So that seems correct. Okay, so let's click the next button here. Now you get a warning in the software that, well, some factors that we have seem to have numeric levels, and then they give us the advice to maybe use an optimal or user-defined response surface design instead. But I will skip this option here. This is not what I wanted currently. So I click OK. The next step is to define our response variable. And the response variable we have is battery life. And the units is hours. And this is also an option where we can check the potential power we have of detecting effects in this design. And the power calculation is based on potential signal to noise ratio we have. And the default value is let's assume we expect to try to detect a signal of 2 standard deviations and the noise is 1 standard deviation. So the signal to noise ratio is 2. Um, if we keep this, the default value, we'll get a warning on the next page. I'll show you what this looks like. But let's just check what we have in terms of power for these for this setting with a signal to noise ratio of 2. I'll click next. And as you can see, we get the warning that we didn't really change the default values of the signal to noise ratio. And we have high power to detect effects that are uh, to double the size of the noise, let's say. So 99.1% chance of detecting effects of that size. So let's just uh, go back and change this to a little bit smaller effect and see what kind of power we'll have. Let's say 1.5. Signal to noise ratio is 1.5, which is a little bit smaller. And let's check the power. It's 88.9%, so it's still quite good, and so on. And this is a potential thing that you can play around with when you want to beforehand check what kind of power your design will have, which can be a very good thing when you design your experiment to have an idea of what kind of size of effect you want to detect and what the possibility for you to detect this effect is with this current design. Okay, but I will follow this example with the design that they have. So I'll click finish here. And now the design matrix is generated. So we'll see we have the material type, the temperature, and then the response that we need to fill out, of course. And we also, so the matrix is ordered according to the run order, which is a randomized run order. So in order for us to get something that we can maybe compare with between different softwares or different versions of doing this, we have to double click the standard order to get it in the standard order. And then the next step is to basically fill in the response values. And I will skip that step and go directly to uh, a version that where I already filled in the response values. Okay, so I will do this. I will go to new design, and will not save this. No, and then I'll go back here, and then I'll click the recent files where I have already the response filled out. Okay, so if you want to follow along with my example and do this in the software yourself, then I'll double click the standard order here, and you may want to pause the video and just simply fill in these values. If you have this, when you have ordered the matrix in the standard order, you can fill out these values and yeah, use the same without going into the book. You have to consider that you will have another run order. So in plots, diagnostics plots, for example, when you look at the residuals versus the run order, they will not be the same as in my example, but everything else should be the same when if you use the standard order and have the same response values. Okay. So there's a couple of interesting options here. You can go to and try to look through these. You can first get a summary of the factors and the responses and so on, maximum values and minimum values and things like that. You can graph the columns before going into the analysis. And you can also get sort of the correlation between different factors. If you're interested in that, they should be like in a typical factorial design. There will be no correlation between factors, but anyway, that might be interesting in some cases. And you also can go into the evaluation and test a model in advance and check before you collect response values. You can check the model. For example, if you run a fractional factorial design, you can check the aliasing patterns for different models that you have in mind and so on. So it's a quite useful options you have in the design stage. But I will go right into the analysis. And the analysis can be made as soon as you have the response values filled out. Okay. And in the analysis pane, if we call it that, you will have sort of a process of analysis set out for you in terms of these steps in the on the page here. So you have to consider first maybe if you want to transform your data, then you will go into the effects and check them, and then the ANOVA pane, diagnostics, and model graphs. So the idea is you follow this process first by considering the transformation and so on. So when you come to the diagnostics, for example, you may have to go back and see, okay, there's something strange with our model. Let's try to do a transformation. Then you have to go back, do the transformation, and redo the analysis steps once again. I will not go into details here about the transformations. We will do that later in the course. But let's go and check the effects. In this version of the software, you will get actually a half normal plot of the effects. Even though this is not a two-level factorial, you will have this half normal plot option here. An interesting thing is that you can select and deselect effects here that you want to try to keep in your model. You have some options here. You can do the same here. Let's say you want to have these as errors and only keep the material type in the model and so on. So there's different options for you to put in and take out terms in your model, let's say. To have the same and to check the ANOVA table with the example in the book, you have to keep A, B, and A, B in the model, and then we'll go into the ANOVA and check to see what we have in terms of p-values and so on. Here, first also, we have some options in terms of layout. So let's say we want to split it this way or this way and so on. It's only a matter of how many tables and things you see at once. So let's use this as an example, but you can choose yourself. Here you have the ANOVA, and we have the p-values, and as we already looked at this and see that all the p-values are quite low. So the main effect of material type, the main effect of temperature, and the AB interactions are all significant, at least if we work on a 5% significance levels, let's say. These tables, you also get sort of a help text from Design Expert with a lot of interesting information that is really good, especially in the beginning when you start using the software, to learn what to look for and to learn more about design and especially analysis of experiments then. You can turn these annotations or help texts on and off by clicking View Annotation, take them out and show them. It's a good idea to have them shown at least in the beginning when you try to learn the software. In this area, you have the fit statistics such as R squared and adjusted R squared, predicted R squared, and so on. You can get the coded equation, an actual equation, and the coefficients in the model in these panes. Okay, so the next step is to look at the model diagnostics or model adequacy check. Also here you have the possibility to change the layout to something that you would like. You can look at one plot at a time if you would like that by changing the plots here. So I will not go into these details so much, we already looked at them, but you have the normal probability plot of the residuals. You have some residuals versus predicted, residuals versus run, which might be different in your case if you have another run order, and residuals versus factor here. And then you have a couple of plots, Box-Cox plot and predicted versus actual, which is supposed to help you or guide you in choosing maybe a transformation in this pane. And then you have some plots here which are related to influential points in the design, let's say. We'll come back to these things later on. Okay, and finally we have the model graphs. And as you can see, you can have a contour plot and all factors and one factor at a time and so on. The interaction plot, I think we looked at this before, and to get it to look like the plot in the book or close to the plot in the book, we have to change the axis here. So we have temperature on this axis, and this can be done by right-clicking and put temperature on the X1 axis. Okay, so that solved the problem. So now we have temperature here, and we have battery life, and we looked at this before and thought that maybe the third material type here, the blue one, is the best because of it has higher battery life on the higher temperatures and quite close to the highest battery life on the lowest temperature. And then we also have possibility to do contour plots, which is not really exciting in the categoric case. We can look at the predicted versus actual again, and we can look at the 3D surface. So, and this can also be rotated and to see that we have, let's see, we can change this to have it look like something that we saw before. Okay, so we have material type here. The third material type is the blue one. The second one is the green, and the first material type is the red one. And as we saw before, the second material type and in combination with the lowest temperature actually has the highest battery life. But it looks like the blue, the material type 3, is better because it's sort of more robust. It performs better in overall, let's say. But that can be, of course, be discussed. Okay. Okay. And then let's quickly look at other options that you have. After, let's say we're done with our analysis and we want to do some optimization. We have the optimization pane. And let's assume we would like to have the computer tell us where is the maximum. What is the combination of temperature and material type that gives us the maximum battery life? It should be material type 2 and the lowest temperature, right? So we can do this numerically, which might be an option in more difficult situations. So we go to numerical optimization, and we let material type and temperature, which are the factors, we let them be in the range of their low and high values, or the 3 levels that they have. And we put battery life. The goal is to maximize it between some limits and weights and importance. These are not really important now when we only have one response variable. And then we check the solutions. Okay, so in order to maximize battery life, this numerical solution says we should have material type 2 and low temperature. And that gives us a predicted value of 155.75 hours. Okay, so that can be a really useful thing when you try to optimize your model after the design. And then in the post analysis, there's a couple of things. We will not go into these in detail now, but you have possibilities to do point predictions for certain uh, settings of the factors. You can do confirmation runs and get an idea of if your model is actually doing good in terms of predicting the behavior that you're expecting, and so on. But I'll stop here with this example, and I hope that you through this get a feeling of how you can run Design Expert to design uh, a an experiment and also to analyze it. Okay, thank you for listening. My voice is running out here, so I guess it's better that I stop. Thank you. Bye bye.